Alright, I'm going to walk you through how to test your Lab 7. So remember, you have to generate your program file from RATSIM. So you go ahead and put in the program that we're testing, which is the InMove sub out and branch program, into your program, or rather into the RATSIM. Hit assemble. You can make sure it works by running the simulator. So let's put in a value of 2 for the input. On the import, you can check the import over here at 202 went in, and then we're going to end up subtracting 1 from it and outputting it to the LED port, which is port 40. And as you can see on the out port, it got 1, which was just 2 minus 1, so it's working. So the program was generated in whatever folder you had this file, this RATSIM file, saved in. So if you go back to your ISE folder, what you should have there is your RAT wrapper that contains your RAT CPU that contains all of your files. Now, I have a few more files than you do because this is a completed CPU design, so you should not have the scratch pad or the stack pointer or the interrupt flag. So these 3 things you would not have in your design right now. But you should have everything else. You notice that I don't have a program right now, so I need to go ahead and add that. I'm going to say add copy of source, and go find that folder where I had my RATSIM, which I think is in my C drive. So it's wherever you had your file, and you can check to see that it is the right program file by checking the timestamp of it. So I just ran that, so this program.vhd here is the one that I just generated. Okay, put that into the project. Now I have all the files I need, and I can go ahead and synthesize. And it does sometimes take quite a long time. Hopefully it won't take too long. Sometimes you're going to want to pay attention to these warnings. We'll see if we have to. I'm going to go ahead and test it and see what goes on. So in order to test the file, I need to create a test bench. I'm going to call it test bench 2 because I've already tried one. VHDL test bench. And I mentioned that you only really need to do a test bench of the CPU, but because the CPU is contained in the wrapper, it's fine to do it on the wrapper as well, because then you could just check every single level. So I'm going to go ahead and do the test bench for the wrapper. Okay, and in the wrapper, I have a lot more things in this wrapper because, again, this is a more completed design, but it will still give you an idea of what you have to do. What you need to do is give this computer an input, and as you can see from our code, it's going to get an input from the switch port or from the switches. So what we have to do is assign the switches some value. So I'm not going to have such a long reset state here. I'm just going to go ahead and just wait for 10 nanoseconds in the beginning, and then start giving the switches a value. So I'm going to say switches gets, let's say 000000100, and that would mean I'd expect the LEDs to get a 3, a decimal number of 3, because a decimal number of 7, because there we go. 8, this is the binary representation of 8, so 8 minus 1 will give me a 7. I'll wait it out for a while, and then I'll change it. Let's try 50 nanoseconds, and then we'll change the switches to some other value. Okay, how about we try the number 14, so we would expect LEDs to get 13. Okay, so that looks good for a first test. Notice we don't need to put in anything else. We're just going to have the CPU run and see if the LEDs can get the right value. So go over to simulation. I'm going to click on test bench 2 and simulate. First I'll do a check syntax to make sure I didn't make any mistakes. Now I'll simulate the model. And I've got got a whole bunch of these signals that I'm not using. I'm going to go ahead and get rid of them. You can click on any signals you don't want to see by doing a click and then a shift click. We do want the LEDs, so I'm going to delete these signals, delete these signals. Okay, so actually things are looking fairly good. We have here 14 on the switches and 13 on the LEDs. So let's see if that worked correctly. I'm going to zoom out a bit, or rather, let me just zoom to the beginning. Okay, so we see that we first set the switches to 8, and how many cycles later? Well, remember one clock cycle is 10 nanoseconds, so we set the switches to 8 at 10. So we had 1, 2, 3, 4, 5. I guess I should be looking at the rising edges. 1, 2, 3, 4, 5. Rising edges later, and we still don't get a value on the LEDs. It took even longer. 6, 7, 8, 9, 10 rising edges. So why did it take 10 clock cycles to go from the input to the output? Well, let's see if we can figure out why. Well, if we go to our code, back to our code, we have 1, 2, 3, 4 instructions. And every instruction takes 2 clock cycles. So before we're going to be able to get an output, we're going to need to have at least 8 clock cycles go by. So why did it go by 10? Well, in order to understand that a little better, we need to start looking at our signals to see what's going on. Okay, so how do you drag out more signals if you want to look at them? Okay, so on the left, you will see test bench 2. If you click on the little arrow, you will then see UUT for unit under test. And that's going to be your full RAT CPU. Under that, you can see the CPU and all the ports for that, and under that you can see all the components in the CPU. So this is really helpful because it'll let you drag out signals that you might want to look at. So the first signal I want to look at is the program counter. I'm going to pull out my program counter so I can see how that changes. And I think since I am manipulating register 10 and register 11, I'm going to pull out those registers as well. So they're in my register file, and here's register 0 to 31. I'm going to pull out register 10 and register 11 so I can look at how those are changing. And let's see, what else might I want? I think that will be good for now. Oh, well, I'm doing a subtraction, so maybe I want to see the result of the ALU to see if that worked. So I'm going to go to the ALU, and I'm going to pull out the result, which I called sum. So after you pull out signals, in order to be able to see them populate, in the console window, you can type in the word restart, and that will clear the screen, and then you can run it again by hitting run. Alright, so we've got some values here. Let's bring this back to the beginning. Notice that it only ran for 100 nanoseconds. If we wanted to run this longer, we could just type run again. It'll run another 100. We could run it for much longer if we just put in like run 1000 nanoseconds. So you have the option of doing that. I'm going to restart that again. Restart, and then we'll just run for the first 100 nanoseconds. Okay, so let's check out what's going on. First thing we want to look at, sometimes it's helpful to see these values in a different radix. I like to look at them in decimal sometimes, like the counter is really helpful to see in decimal. Let's go for unsigned decimal, and let's go ahead and put the switches and LEDs as well in unsigned decimal. And the register contents, yeah, why not? Let's put everything in unsigned decimal. So you can look at whatever radix you'd like. Let's see what's going on. So notice that the counter started at 0, but in my code the instruction starts at 1. So the first instruction that I get is going to be nothing. So I'm going to waste a cycle right there of doing nothing, which is why, remember we said that it took 10 clock cycles to get a result. That's because we had to start our counter at 0. So even though we only had 4 instructions, it had to run, since I started my counter at 0, it had to run that 0th instruction, which did nothing because there's nothing there, and that's why it took an extra 2 clock cycles to get us to 10. Okay, so my counter had started at 0 because in my code I had set the counter to 0 initially, but I advised you to set it to 1 initially so you don't have that extra clock cycle. And then we could see the PC counter changed to 1. And then it remained 1 for 2 clock cycles, because remember we have to do the fetch and execute. And then it changed to 2, and then it changed to 3, and then it changed to 4. And if we run this again, you could see then it changed to 5. And our last instruction was a branch, and it branched back to 1. So it's always really helpful to look at your program counter first to see that it's doing what you expect it to do. So if you did a branch, it better branch back to where you thought it should go. Okay, so might also be helpful, I think that's, yeah, let's start with that. So the first instruction is the move instruction. It's the in instruction. So the in instruction, we are expecting it to get the value on the switch port to go into R10. So after the switch, the first instruction is completed, which is over here, the value that is on the switches should go into register 10, and that did occur. So that looks good. Then the second instruction is the move instruction. So we're expecting at the end of the move instruction for the 1 to be put into register 11. So at the end of the move instruction we have 1, there we go. Oops, there it is, 1 into register 11. That looks good. And as you can see, this is the execute cycle of the move instruction, and the ALU put the value of 1 onto its output, which then at the rising edge got put into register 11. So we can see that transfer occurring right here. So when we executed the move, the ALU result was a 1 that got sent back to the register file, and then at the rising edge of the clock, boom, it got put into the register. Okay, so then our counter was 3, and that means we are going to the sub instruction. So again, we're going to expect to see a result on the ALU, and then a cycle later that result should show up in R10. So the result on the ALU of 8 minus 1 is 7, and boom, at the rising edge, 7 shows up into register 10. That looks really good. Okay, the fourth instruction is an out instruction, so we're going to output from R10 to the LED port. So we should see at the end of the out instruction the value that was in R10 be put to the LEDs. So here we go. There's the LEDs up here, and what was in register 10 at the end of the out instruction is put onto the LEDs. So that works great. And then, as you can see, we start over with the in instruction. So the first instruction, 1, is the in instruction, and so we're getting the value from the switches and putting them into R10. The switches at this point is 14. So at the end of the in instruction, 14 is the value in register R10. And so forth and so on. So once we start here from the in instruction, now we only need 8 cycles later. So let's see, run, in order to get the output of 14 minus 1 onto the LEDs. There it is right there. And so that only took 8 cycles instead of 10, because remember we didn't have to execute instruction 0 like we did the very first time around. And also you can see that when the ALU is not doing anything, which is during all these fetch cycles, the output of the ALU is garbage, because it's taking in garbage data and it's outputting something, but you're not doing anything with it. So that's why you're seeing X's show up during the fetch cycles of the ALU. And sometimes it shows it as green or red. It should show all X's as red, but sometimes, as you can see here, it's showing it as green. And then the U, the LEDs are undefined up until we get the first output to the LEDs, because we haven't assigned anything to the LEDs until they got to the out instruction. So that's what the U is meaning. So this is an extremely useful tool to see if things are working correctly. And what you're going to have to do as you're debugging your system is pull out even more signals. So if you're not getting, like for example, if I did not get the value in my move instruction, which was instruction 2, so if I didn't get 1 into R11 by instruction 2, which was right here, I might want to check out what's going on in my ALU, or maybe what's going on in my register file. Maybe I set a control signal incorrectly, so I can start pulling out some more values. I can look at my ALU select value to make sure that I selected the move value. I can look at my register file write select or write enable value to make sure that I was writing. So you can use this tool to check out what signals are happening at what time to figure out why something maybe occurred or did not occur when you expected it to. And it really is a very step-by-step process. You need to have a good understanding of what the code is supposed to do and go step by step in iSim, making sure that all the values move around appropriately. And if you find that they don't, looking really into each control signal that gets you there to make sure it was set correctly. So that's the process of going through debugging for your Lab 7, and hopefully you will end up getting a screenshot that looks something like mine, that you get your LED values to be -1 of the switch values.